In this video, we are going to solve a very interesting problem in projectile motion. This problem is called as the basketball problem. I have named this. Now, what is so important about this problem is that by the end of the video, when we have solved the problem, we will have obtained a very important equation in all of projectile motion concept, okay, which is the trajectory equation. Let us read the question. A basketball is shot from a horizontal distance d away from the base of a basketball hoop as shown in the figure. As we can see from the figure, this is the basketball hoop and this is the basketball, and this is the velocity vector of the basketball, perhaps thrown by a player or someone, and this is the angle, the initial angle that is relative to the horizontal. This is the distance between the basketball and the basketball hoop, or the base of it, and this is the height. Okay, pretty much straightforward. Now let us continue. If the ball is launched with an initial speed vi at an angle theta above the horizontal, at what height h does it enter the basket? So this question, or this problem, asks us to find an expression for the height of the ball. Okay, so how can we do that? Well, let us see. First of all, let us decompose the velocity vector of this ball into its own components, namely the horizontal component and the vertical component. Now, this part is the horizontal component, and this part is the vertical component. The horizontal component is given by vi cosine theta, and the vertical part is vi sine theta. Okay, so in other words, we have vyi and vxi. Okay, vyi stands for the initial vertical speed and vxi stands for the initial horizontal speed. Okay, so the vyi part is basically vi sine theta, while the vxi is basically vi cosine theta. Okay? Now, we know that one of the vertical kinematic equations is this. Y final is equal to y initial plus vyi times t minus 1 over 2 gt squared. Okay? Now, we know that y final is basically just the height. Y initial in this case is 0. Why is that? Well, basically this is our frame of reference. This is where the motion takes place. Okay? So at this point, the height of the ball is actually at 0. We are not measuring from here, from the ground. Remember that. We are measuring from this point, our frame of reference, or basically the frame where the motion starts. So the height from this point is actually 0 relative to this. Okay? Or relative to this imaginary ground. You can call it as a ground for simplicity's sake. Now, so also we know that the vyi part, this part, is basically this one. Okay? Thus, we can now substitute all of these three into the equation. See what we get. Height is equal to 0 plus vi sine theta times t minus 1 over 2 gt squared. Okay, so basically what we have got is this. Let me just get some space and let us just move this to here. So what we have got is actually this equation. Okay. Now, you can leave it here as it is. But what you get is basically the height in terms of time, or the vertical position is a function of time. It depends on time. But we can do better than that. We can actually express it in terms of distance, which is much better and much simpler to work with. Okay? Furthermore, we know that at any moment, time is sensitive, it changes, but the distance does not change, provided that for short distances, of course, because for long distances, you know, the Coriolis effect may take in place and other factors may take in place, okay? So we know that distance is actually speed times time, but for this distance, all right, what I mean by distance is basically the horizontal distance, okay, is this. D is equal to VI cosine theta, all right, times time. Or time is basically D divided by VI cosine theta. Now, if we substitute this time into the equation, we can eliminate the time, and thus we can get a clean equation that basically calculates for us the trajectory path in terms of distance, not time, which is basically much simpler and much better to work with. Okay, so let us see what we get. Now I'm going to delete this part and just substitute the time. We get basically VI sine theta, okay, times D divided by VI cosine theta, okay, minus 1 over 2 G, and all multiplied by D divided by VI cosine theta, all squared. Notice that the VI parts will basically just cancel. Sine theta divided by cosine theta is just tangent theta. So we get D tangent theta minus 1 over 2 G D divided by VI cosine theta all to the square. Now this is the trajectory equation. Okay, if I just get rid of all of this. So what we have obtained, what we have just obtained is basically the trajectory equation. Now this equation works as long as we have a short distance, okay, because for long distances, Coriolis effect takes place, and furthermore, gravitational acceleration deviation, because we know that with altitude, gravitational acceleration changes. Okay, this G is not so constant that what you think, okay? But for short distances, it will work. And furthermore, another note, another condition, provided that air resistance is neglected, okay? After all of these conditions provided, then this equation works nicely, okay? So this is the trajectory equation. I encourage every student to solve this type of problem or tackle this type of problem, because by the end of it, you get an equation that is so much important in all of projectile motion. Okay? And that's for it.